G'day, in this video we're going to be looking at a bunch of different formula that we can use to describe the energy changes in planetary orbits. Particularly our focus is going to be on deriving those relationships. Now in this video we're going to be looking at dot points 5.3.4 and 5. Our focus is on finishing off inquiry question 3 and module 5 for that matter. We're looking at how the force of gravity determines the motions of planets and satellites, particularly applying to energy concepts. There are a bunch of different formulae in dot point 5 which we'll be exploring today. A key intention is to be able to derive these formula, as the vast majority of them are not actually found in your datasheet, meaning that you do have to have an understanding of the physics behind a lot of this stuff in order to apply a formula that we've already learnt about and that's already in the datasheet to these specific scenarios and be able to get some relationships between variables going. Primarily, we'll be looking at the relationship between a satellite's kinetic energy, its gravitational potential energy, and its total energy. So in a previous video on Kepler's laws, we looked at second law in particular. And in this section, we were discussing the idea that for an object which is orbiting in a non-perfect circle, some sort of ellipse, there's going to be periods of high speed and low speed. And therefore, as we know that there's a direct relationship between speed and kinetic energy, there are points on the orbit where there is high kinetic energy when there's high velocity and low kinetic energy when there is low velocity. In an area close to the central object, we're going to see the highest kinetic energy and the lowest gravitational. And conversely, when the object is really far away from the central mass, the opposite is true. The orbiting object loses kinetic energy, but as a result gains gravitational potential energy. It's really important to start noting here too that we're going to begin to refer to this idea of total energy. And this represents the energy of both the kinetic and the potential. So when an object is orbiting, it has both kinetic and potential energy at the same time. And we say that the total energy is essentially the kinetic plus the potential. And a key principle which is going to be really important to carry through in any of these activities when we look at energy is that we run with the assumption that the total energy of the object orbiting is constant as long as we are undergoing some sort of stable orbit where the object is following a set path. A key concept in this topic is to analyze gravitational potential energy of objects which are in orbit. This analysis requires us to know either the gravitational potential energy that an object currently has or a change in gravitational potential energy that it undergoes. So far in physics topics, we have relied on this near-Earth field approximation in most circumstances. It's this idea that even though Earth's gravitational field is radial around the Earth, in any local area right at the surface of the Earth, we can assume that the gravitational field is parallel at all points and is constant in magnitude. These assumptions are quite important in being able to simplify a lot of the mathematics and physics that we use when analyzing forces of motion on the surface of the Earth, and we find that within a reasonable degree of accuracy that these assumptions remain true at the scale that we're talking about at near Earth. However, we're going to be starting to do some analysis with gravity and gravitational potential energy using this model here. We have a radial field, and essentially that field decreases in strength the further away we get from the Earth, and that's comes back to our idea of Newton's law of universal gravitation. So in this instance, we'll be applying Newton's law of universal gravitation to be able to describe potential energy and potential energy changes for objects in orbit. Just to get our minds thinking in the right direction, I first want to use our more familiar near-Earth orbit to demonstrate how gravitational force is directly related to changes in gravitational potential energy. So in this diagram, I've got the flat surface of the Earth, and we have parallel sets of field lines which are showing our gravitational field, and We have an object in that field set above the ground at height h. Now we know if we place that object in our gravitational field, it's going to experience a force which is equal to mg. And if we want to relate this force to a type of energy, we can relate energy and force through our work equation. We know that work is done on an object by applying a force over a set distance as it moves. With some of the information above, I can restructure my work equation into something that might look a little bit more familiar to you. By replacing the force in the formula for mg and the displacement for the height that the object can move through, we can therefore conclude that the work done on an object if it falls due to gravity is equal to its mass times the gravitational acceleration multiplied by the height that it's dropped from. Therefore, if we get the object from its maximum height to the surface, that the work formula then calculates for the energy applied to have that work done. So if we assume that all of this work that's being done is reducing the potential energy and that there is a one-to-one transformation from potential to kinetic energy, we can therefore run with the assumption that the change in potential energy that is experienced is equal to negative mgh, a formula that you should be quite familiar with. However, things do not become as simple when we move off the surface of the Earth. Now we need to start thinking about our gravitational field being, one, radial, but also that this gravitational field weakens the further away we get from the central mass. If our object moves towards the central mass, then gravitational potential energy will decrease. And if the object moves further away, then gravitational potential energy will increase. Now, to get a formula which describes gravitational potential energy using this model, we're going to have to run with a few key concepts and assumptions. First off, we already know that the change in gravitational potential energy will obviously be the value of the final gravitational potential energy subtracted by the initial potential energy that the object has. But this assumption here that's already been pre-written is an interesting one. We know that attraction due to gravity occurs at all points in space. Therefore, the conclusion that we need to make from a quantitative perspective is that gravitational potential energy could only have a zero value if the distance between the two objects r was infinite, at which point there would not be a gravitational pull between the two objects. Now, this has some very interesting implications for the value of u. Now we have our central object here, and let's say that we had a point which was infinitely far away, that r is equal to infinity. At this point, if we had our orbiting or interacting object here, its initial velocity would be assumed to be zero at this point. If we were to move towards our central object, we've already identified that our gravitational potential energy will need to decrease. But we've already said that the gravitational potential energy started at zero, meaning that a decrease in gravitational potential energy will mean that we are now talking about a negative energy. And this is partly the reason why we can explain that gravitational potential energy is always negative at any point in real space. In other words, when the distance between the two objects is less than infinity. This is actually demonstrated on the graph that is here on the right, where you can see that our potential energy is always below the zero line, no matter what radius we're at. And that as our radius approaches infinity, the gravitational potential energy is approaching zero, just like has been demonstrated here in our diagram. Now we know that the change in gravitational potential energy is equal to negative mgh, but in this case I'm going to write mgr, the distance between our two objects. We also know that by Newton's law of universal gravitation, that the force experienced by an object in a scenario like this is not only equal to mg, but is equal to gmm on r square. Rearranging our formula, we can cancel out our two masses for the smaller object and say that g is equal to g m on r squared, a formula that we have derived in previous videos. This value can then be substituted into our base equation so that we now have an expression for the change in gravitational potential energy, not in terms of g, but rather in terms of the mass of the central object and the distance that the orbiting object is from the central object. Now, you might notice that this formula for delta U is the same as the formula in the datasheet for U, the actual value of gravitational potential energy. This is a little bit, I guess, convenient that both of these values are equal to each other, but it is really important to show how and why the value of gravitational potential energy yields the same expression on the right-hand side. So we know that the change in gravitational potential energy, as was written up the top, is equal to the final gravitational potential energy minus the initial gravitational potential energy. And that if we know that the initial gravitational potential energy is equal to 0, just like in our scenario at the top, we can therefore conclude that the change in gravitational potential energy, as we move our object from an infinite distance towards the central mass, would therefore be the same as whatever the final gravitational potential energy is. Therefore, as our formula shows in the datasheet, as it shows in the datasheet, the gravitational potential energy for an object any non-infinite distance away from our central mass is going to be equal to negative gmm on r. So currently, we now have an expression for gravitational potential energy. We also want one for kinetic energy. Non-surprisingly, this formula is going to be based on our k equals half mv squared formula. But in order for us to be able to have an expression for kinetic energy in terms of the masses of the orbiting objects and their radius, we're going to need to be able to express the velocity of the object in these terms. The way that we can do that is some simple circular motion analysis. If I have our central mass and we've got an orbital path and we've got an object on that path, we know that we have a centripetal force, which is also the gravitational force. This just goes back to our circular motion concepts and some of the earlier concepts that we looked at in this third inquiry question. And so we can run with the assumption that the centripetal force that the orbiting object is experiencing is all coming from the gravitational force caused by the central object. As such, we can write an expression for centripetal force. As well as our expression for gravitational force based on Newton's law of universal gravitation, and then rearrange for V. And there we go. We can say that the velocity of an object orbiting a central mass is going to be equal to the square root of the universal gravitation constant times the central mass divided by the distance between the two of them. Now, this is actually quite a helpful formula. It's found its way into a bunch of different HSC questions, but importantly, it is not in your data sheet. You are expected then to either recall this formula or even better, be able to derive it quickly just as I've shown here. The most important thing that you need to be able to recall in order to do that is that if you need an expression for the velocity of an orbiting object based on the central mass and the distance between the two objects, you need to run with the assumption that Fc is equal to Fg. If you can remember that, you can then rearrange quite readily to be able to get this formula. But that part in red is the key concept that will get you there. The math then just follows. So, knowing that the kinetic energy of any moving object is half mv squared and that the velocity of an orbiting object is the square root of gm on r, developing a formula from here is quite straightforward. We simply just need to substitute in the velocity value into our kinetic energy equation. And that is that the kinetic energy of an object in orbit is equal to gmm on 2r. Again, this formula is not in your data sheet, and if you were to need it for any reason, it is a simple formula to derive. However, you need to know how to express the velocity of an orbiting object. And again, that comes back to knowing this formula, which is also not in your datasheet, referring to the previous slide to figure out how to derive that if necessary. Unfortunately, a lot of these formulas look quite similar, and you are going to have to rely on some method of being able to pull out these formula if and when needed, because you will not have your datasheet as a reference as you usually would for calculations within the scope of this course. So now that we have an expression for the potential energy and the kinetic energy of an object in orbit, we can now start to describe the total energy. This one's pretty straightforward. As stated before, the total energy of an object in orbit is simply the sum of its potential energy from gravity and its kinetic energy. We also know the relevant expressions for these two. The formula for potential energy is in your data sheet, but again, our kinetic energy formula is not, nor is our total energy, but at least that one's pretty easy to remember. It's simply, by definition, the total energy is the sum of the potential and kinetic energies. We can write a little bit more of an in-depth expression for total energy by substituting in the U and K expressions. We can simplify this expression further by adding the two fractions. However, they do not have a common denominator. We will have to take our left fraction, the one for potential energy, and make sure that the denominator is common with the second fraction. We can achieve this by multiplying by 2 on top and bottom. That may be something that you haven't done for a while. So when combining those numerators, essentially we have negative 2 GMM plus GMM, which gives us negative 1 GMM, meaning that our final expression here is negative GMM on 2R. And that is our expression for total kinetic energy. Now, there's a couple of interesting little bits that we can do with this formula, and we should be able to notice that this formula for the total energy is remarkably similar to the formula that we have for U and K. There are two key assumptions that we can make. One is that the total energy is half the potential energy, and that the total energy is always equal to the negative of the kinetic energy of the orbiting object. Keep in mind also that none of this is in your data sheet either, but may be knowledge that you have to refer back to within a problem-solving question. Finally, we have escape velocity. This is a set value that describes essentially the velocity which would be high enough for an orbiting object to escape gravitational attraction. Essentially, if it hits this velocity, it will start to move along a path in which it is no longer orbiting. From an energy perspective, what that means is if we have achieved escape velocity, the kinetic energy of the object is greater in magnitude than the potential energy of the object. And by consequence, what that means is that the total energy is greater than 0. However, if we're looking for that minimum required velocity, that turning point or cusp, this is going to occur when the kinetic energy and the potential energy are the same, and therefore the total energy is equal to 0. So if we were to write an equation, it would look something like this. Now, we're not going to worry too much about the total energy. We're much more focused on the sum of K and U being equal to 0. So what I'm going to do is substitute in our half mv square. Now, the reason that I want to be able to put this into the formula is because we want to calculate for a v value. So our equation has to have v in there somewhere. I'm going to add that on to our gravitational potential energy, negative g mm on r. I'm going to say that those two summed together is equal to 0. From here, we can rearrange and solve for v. And we find that the escape velocity is equal to 2 gm on r. Again, this is a formula which is not in your data sheet, but does get called on quite a bit in the HSC. The key thing that we need to remember, though, to get to this equation is that K plus U is equal to 0 when we've hit that breakpoint for our escape velocity. Once you know that, you already know what K and U are. Both of those are in your data sheet. It is just a matter of being able to put those two expressions in, rearrange, and solve for V. Just finish here with a summary of formula. There are a lot of them, and you'll notice that unlike the rest of the course, a lot of these formula do not show in your data sheet. However, you can be assessed on them. You might be asked to derive them. You might be asked to apply these formula even though they're not right there in front of you. It will take some effort, one, to learn how to derive them, and two, to be able to recall them if needed. But this is some effort that you're going to have to put in yourself in your own time. We're also going to be spending a handful of lessons having a look at problems which involve these formula as well. Speaking of, our next video is going to be about solving problems involving energy changes in planetary orbits. But until then, have a good one.